Good afternoon, everyone. On behalf of Partners in Project Green, I would like to welcome you to our monthly series of green technology webinars. For those of you who might not know, Partners in Project Green, developed in partnership with Toronto and Region Conservation and the Greater Toronto Airports Authority, is a growing community of businesses working together to green their bottom line by creating an internationally recognized eco-business zone around Toronto Pearson. So let's begin. This month's Green Technology webinar is focused on motor management. We are very fortunate to have Herb Sinnock from Sheridan College joining us this afternoon for the second time to give us an overview of a proper system design and identifying inefficiencies in motor management. Herb is a manager of applied research and sustainability for the Faculty of Applied Science and Technology at Sheridan College. As a certified energy manager, he spends a lot of his time at local manufacturing and commercial facilities assessing and identifying opportunities for energy and production efficiency. So you get to get on now, Herb.
Thank you very much, Alex. It's my pleasure to talk with you about this subject today. It's certainly one that's important in industrial facilities. So let's kick it off right away with this question of why do we care about motor energy use? And fundamentally, we see that motors can be attributed to a large portion of the use we see in the industrial sector, up to 75% in the Canadian context. And in North America and Canada, about half of electrical energy is consumed by motors. The next question I guess you'd ask is, why is that number still so high? And really the reason is that motors are integrated into our manufacturing processes. And because of that, it can be very difficult to figure out what kind of loads they should be sized to do, how they could be sized smaller. It's very difficult to measure them in place. And so often what we see is motors end up being replaced on a one-to-one basis. So one goes out, another one goes in of similar specification, similar horsepower. And what we aim to do today is to give you enough information that you can ask some good questions of your suppliers and to take some additional consideration and thought when you have an opportunity to replace a motor in a process somewhere. In this webinar format, I will tend to throw out a lot of concepts, but I try to relate all of these back to three key principles. And the webinar is being recorded, will be posted for viewing afterwards, so you have a chance to review, and my contact information will be on the last slide. So if I blaze by something and you'd like a little more information, feel free to send me an email or ask me a question after the fact. I've included a background slide or two just to review some of the concepts that come up when we're discussing motor issues. And the first one that always comes up is the idea of power factor. An induction motor, like we see in most facilities, will require both real and reactive power. The real power is the stuff that we measure with our energy meters. It's the stuff that creates work and heat. It spins the motor, it lights lights. The reactive power is what we use to establish stored energy fields, like magnetic fields that we need in order to get the motors to function as they're supposed to. So our induction motor is going to end up consuming the real power to actually spin the rotor. It's going to consume the reactive power to create the magnetic field. And in the diagram on the left here, what you see is this definition of real power as watts or kilowatts. The reactive power is measured in VARs, volt amperes reactive, or kVARs, depending on whether it's thousands of volt amperes or just VARs. And this is a right angle relationship. So you can see on the top right that apparent power is described as the square of the real power and the square of the reactive power. Take the square root of that to get the apparent power, or the hypotenuse of the two. So there's a relationship there. And kVA will be the amount you get if you were to clamp on your ammeters onto your lines and take voltage readings and multiply your voltages and currents together. And actually represents, in effect, what the utility has to supply to you in terms of current to actually get your facility to work properly. When you divide that kVA number into the reading you get from the kilowatt meter, what you're getting is power factor, essentially a measure of the proportion of reactive power that's being supplied to your systems. So your induction motors in your facility are going to significantly lower power factor, and your utility is paying attention to that and will often levy a penalty if it sees power factors drop below 90 or 95% in your facility. So they're definitely watching that. I want to talk also about the various types of motors we see out in practice. So in fairly small percentage, we see synchronous motors, about 1 to 2% of the applications. The synchronous motor has a wound rotor, so the spinning part has windings on it. The stationary part has a number of poles, and its operating speed is tied to fractions of the frequency it sees. So, for example, a 60 hertz motor with a base set of poles would spin at 3,600 RPM. If you added more poles, it would spin at 1,800 RPM. And then you could add more poles, it would spin at 900 RPM, but it's always tied an even frequency to that electrical frequency incoming. The interesting feature of a synchronous machine is that you can actually configure it to supply reactive power to the system even while it's running and consuming real power, so that a synchronous motor actually gives you the possibility of correcting power factor in your facility. That's also incidentally the generator of choice for an electric utility, because they're able to create real power and reactive power at the same time and actually balance their systems in terms of real power provided and reactive power. But synchronous motors are expensive, and there are a lot of options available these days for providing the same kinds of things that a synchronous motor can. So that's why we see such a limited rollout of those. Direct current drives are sort of the next most common in there, about 3 to 4% of install base, maybe even 3 to 5%. They're historically used for things like precision speed control, applications requiring high torque or rapid starting and stopping, servo motors, things that require accurate positioning. But they're historically have been considered high maintenance, particularly the ones that had brushes, because the brushes have to be replaced on a regular basis, as do slip rings. They have to be disassembled and reassembled. And these days, you might effectively replace the functions of a DC motor drive with an AC variable speed drive, which I'll get to in a little while. That said, there are now a number of brushless, electronically commutated DC motors, so they don't have slip rings, they don't have brushes, they don't have those moving wearable parts. And these motors now have excellent power switching technology that essentially does the same function. So now they can be high efficiency, they can be very highly specialized. Things like stepper motors that move in precise angular increments, and precision positioning and angle. By far, though, in the marketplace, what we're going to see is AC induction motors. They're about 95% of the applications we see. They're the workhorses. And in this case, the reason they're so popular is that they just simply induce a magnetic field, a rotating magnetic field in the stationary part of the motor, which drags along a very simple rotor construction that's a lot like the hamster wheel that you see in your hamster's cage for exercise. So with that very simple construction, there's not a lot that's going to fail on the rotating part of it, apart from bearings and things that are around the rotating part. And that simple construction also keeps the cost down on the item. The disadvantage of the induction motor is that it's going to consume reactive power, creating its magnetic fields, and it's going to create what we call a lagging power factor. The rotor will also typically spin a few percentage RPM below the rotating electric field, because it's essentially, the rotor is essentially being dragged by that rotating field. So it has a torque characteristic that will see it essentially hold its speed within a few RPM until it reaches a breakdown torque, breakdown threshold, at which point it'll basically go to stall, and it'll create a condition we call locked rotor. So I'm going to focus most of my discussion today on the induction machines. Before I leave this slide, I also want to talk to you a bit about the nameplates and all the wonderful information that's on a nameplate. Your nameplate is essentially your description of the physical, electrical, mechanical characteristics of the motor. It tells you an incredible amount about what applications are suitable. And if you know how to read what's on there, it's going to tell you a lot about whether you've got the right one selected in place. So here's some of the things you're going to see on a typical nameplate. And if you look at the one in the top right, you can see that it indicates next to the word service factor, there's a 1.15 and then a small indication of three-phase. So it's indicating three-phase. You see 460 volts below that, 60 hertz. So it's told you that this is the electrical service it's expecting, and it wants to be close to that. It's also going to tell you on the mechanical side the rated horsepower, in this case 30, and then it's indicating amps and RPM, and these are the rated amperes and RPM. So this is its nominal operating range. It wants to be pushing 30 horsepower. It will be drawing 35 amps, and it would want to spin at 1765. The next thing you probably want to find out here is the service factor. That's the number I mentioned first, 1.15, and that essentially says you've got a 15% margin on RPMs, and you could drive this a bit higher. You drive it with a bit more load, and it will be perfectly happy. It won't climb out of its maximum temperature range, and it'll actually serve that. This is not something you'd want to do for a prolonged period of time, but if you had a bit of a surge or a bit of an overload, it could certainly handle that within that period of time. You also see a very important number down in the bottom right, which is the NEMA nominal efficiency. And that's telling you that this high efficient motor is about 93% efficient. And it's important to pay attention to those numbers. As we'll see in a little while, efficiency can make a big difference in your cost. We also see things like class. So there's one called NEMA design. Those go A, B, C, D. They tell you about the torque characteristics of the motor. You see at the top right a frame designation, 286T in this case, which tells you about where the bracket and bracket hole locations and all of the physical size and specification of the motor is. These are all standardized. So you could replace a 286T frame motor with a 286T frame motor, and you're guaranteed you'll have the mechanical fit. So lots of good information on there for you. There are also a couple of key descriptors we see that tell us about the enclosure of the motor, and it really is important to make sure that the motor enclosure suits the application and environment it's in. A totally enclosed fan-cooled motor is much like it sounds. The idea is that you've got an integrated fan for cooling. It's enclosed so it can handle being in dusty and corrosive environments, as opposed to the open drip proof, which is going to draw ambient air into the motor to cool. And that can be used in clean environments where you don't have the dust flying around. And it can tolerate dripping liquids from directly above and 15 degrees off to either side perfectly fine. But you'll also find a number of fairly specialized motor designs as well. So ones for bakery environments, which are dusty, explosive environments, ones that you could submerge or splash. And if you've got those kinds of environments, it's obviously important that you match those enclosure characteristics to the industrial environment if you're going to want them to hold up over time. I want to introduce the first of the three key principles that I think we need to cover. The first is that we really need to consider a motor in the context of its useful life. So I call this slide life cycle, or how I learned to love higher first costs. The facts are that motors tend to cost more to operate over their lifetime than their first cost, and you can see from the graph here that the initial costs are a small piece of this entire wedge of energy costs, other costs, maintenance costs. And I put a little factoid on the side that a heavily used motor might use 10 times as much of its first cost to run in just the first year. And in general, the statistic we might see thrown around in the industry is that 20% of the overall life cycle cost of a motor is in the first cost. So 80% you could attribute to operating the motor. This brings us around to establishing the case for why we might want a premium efficiency motor. Why would we consider that? life cycle thinking actually makes it pretty straightforward to evaluate the economic value of using these. And so I've shown some of the sample calculations that you might undertake. And the formula is actually really quite simple. It's comparison of how many kilowatts you'd expect to consume with a standard efficiency motor minus the kilowatts you would expect to consume on an energy efficient case. And the equation inside the brackets is essentially taking the horsepower rating of the motor, 0.746, which is the conversion to kilowatts, times a load factor, or basically tell us about how often this thing's used, and then you divide the whole thing by the efficiency. So you could imagine that a higher efficiency number in the denominator is going to make this number inside the bracket smaller. And to see that in action, let's take an example where we're replacing a failed 75 horsepower standard efficiency motor, which is 89.5% efficient. There's a load factor of 80% on this in this application. And we're going to replace it with a premium efficiency motor at 94.5%. And you can see from the calculations in the brackets that all that I've really changed, one to the other, is the efficiency in the denominator. And the equation shows that we should have a net savings of about 3.09 kilowatts, and that's the continuous. If I multiply that times the hours of operation per year, in this case it's a 24/7, 365 operation, and you multiply it by your cost per kilowatt hour. Now, and in this case we chose 12.5 cents because that's fairly typical for Ontario and in this area. And that yields savings of $2,900 a year just on making the switch to a higher efficiency motor. Just also another quick note is watch out for the labels. You know, it's still possible to find a motor that's billed as green or energy efficient, but actually really doesn't live up to the label. So you can see here that there's a motor here described as energy efficient. Its efficiencies are in column 2 for 10 horsepower through 200 horsepower. And compare it to a real NEMA premium efficiency motor. You can see that there's a variation of 1 to 2% difference in efficiency, and it would make quite a difference in your dollar savings. The second principle is that we must consider the system and not just the motor. The thing we find is that each system has a system curve or a description of how it operates. And in these graphs, the system curve is the red line. And the red line in the first box is showing us an application where as flow increases, pressure increases. And the second, that we have basically a static pressure, so that even with no flow, there's a bit of pressure in the system, or very low flow, there's a little pressure in the system. And then we have a variable flow and pressure. Then in the third case, what we see is that we are maintaining flow at a constant level and pressure varies up and down. And finally, one where pressure is relatively constant at all flow levels. But in all of these cases, the pump curve in blue is trying to intersect that system curve at the point of maximum efficiency. So all of our components in the system have their own efficiency curves, and obviously we want them all operating at maximum efficiency. There's a few different scenarios that that come up that actually sort of push us away from this optimum point. Since we're often sizing our rotating machinery with a safety factor, we're making it a bit extra large just in case the system requirements change, or just to make sure the thing doesn't come in underpowered, we're automatically pushing the motor curve off that maximum efficiency point. We're then either running that motor at a lightly loaded condition, which we'll see later is not really the most efficient setup, or we find that we need to control the system to align the curve to the motor. Not all of our controls are created equal. To make things worse, as our system ages, the system characteristics change. So first, what we might find is that our turbo machinery, our pumps, our fans, as they wear, are no longer providing the same amounts of flow at the different pressure regimes. So we've moved off that optimal curve. The second thing is that our system may move from a flow versus pressure regime to a steeper one, where essentially, as I've got clogged filters and dusty components, what could end up happening is essentially I'm building more pressure or more resistance to my flow as that system gets dirty. So maintenance is obviously a key factor in here. And you can't discount the effects of things like belt slippage, making sure that things are at correct tightness, using notched belts and synchronous belts instead of V-belts, things like that can help keep us on that optimum point in a longer period of time. And I've included here also just a quick calculation that you can use to keep track of whether there's been changes in your system or whether a change you've made is for a good effect or has had a detrimental effect. The idea is really quite simple. Whatever your key system output is, it could be a sustained flow rate you need to have. It could even be, if it's a cooling system, it may be how effectively are we maintaining set point. But take that key system output metric, divide it by the power you're putting into the system to accomplish that work. And so that macroscopic look will allow you to look at all kinds of things in control, in sizing, in maintenance, and see if they've really had an impact in your system. The two curves here are going to help you understand some of the impacts of your control choices. In particular, significantly oversizing motors in relation to application. What you can kind of see from the efficiency curve is that the motor is going to be perfectly happy between 100% load and even overload to some extent, down to about 40–50% loading. So if you have a very lightly loaded motor, its efficiency will be much lower than the efficiency of the motor running near its rated load. And so it's very important to avoid those situations where you have a machine idling without drawing an adequate load on it. And you can see that also in the power factor curve on the right, that very quickly our power factor drops as we lighten the motor load. And so we can suddenly have a very distinct and drastic effect on the plant power factor by allowing these motors to run lightly. Not all controls are created equal, and there are a number of ways that I can control what's going on with my process. I'm trying to match the motor and the load, remember, and keep at that optimum efficiency point. So historically, some of the ways have been dampers and vanes. And you can see at the bottom left, there's an inlet vane damper. So this is closing the vanes to restrict, say, airflow. In the middle are variable speed drives, which are adjusting motor speed to suit what's going on with the application. We'll talk about that a fair bit. The top right, you see a number of output dampers. So these are controlling airflow on the outlet side. And at the bottom, what you see is a magnetic clutch, or essentially a device that's taking the shaft energy of the motor and providing some variability in how that power is coupled to the load at the other end of the shaft. And this is really kind of highlighting that outlet damper, which I was talking about in the top right of the previous slide, doesn't have very effective control for us. If I'm at 100%, I'm starting at the right-hand side, I've got 100% flow, and I decide I want to dial back that flow to about 50%. If you follow the curve down for flow rate from 100% to 50%, what you'll see is that at 50%, your energy consumption of that motor, your input power, is still up around 70% for an outlet damper. Compare this to variable frequency drive, which scales down in this nice curve so that my 50% flow rate is now at about 20% of the input power. And all of that orange space in the middle is my energy saving potential by picking the right kind of control for that application. That said, This isn't sort of a universal claim that everything should be controlled by variable frequency drive. In this case, what we can see almost straight away is that if our application is somewhere between 100% flow rate and maybe 85% flow rate, the actual difference in input power over that span, even at 85%, is maybe 15–20% of input power levels. We may find in that case the extra cost of the variable frequency drive versus a damper just doesn't make sense, and you can't make the case go. So now I've talked about the variable frequency drive, variable speed drive. These are, in my opinion, basically synonymous. I mean, variable speed drive, variable frequency drive, adjustable speed drive, all names for effectively the same thing. The one possible exception I may sort of state here is that you can control speed at the process shaft both by adjusting motor speed, as in a variable frequency drive, but you can also do it by changing the coupling like we saw with the magnetic drive. So you can adjust speed in a couple of different ways. But just talking about variable speed drives, the idea is really fairly simple. An AC motor is kind of a dumb hunk of metal, and if it sees a certain input frequency, it'll spin in relation to that. So if you slow down the frequency of power coming in, it'll slow down too. The whole idea of the variable speed drive, the electronic controller on the feed side, is to take the 60 hertz frequency that's coming in and change its frequency. And in so doing, it changes the motor speed. Why do we care about variable speed drives? What makes them so attractive? Well, really, it comes down to these affinity laws that I'm presenting here. And they're not even really laws. They're sort of affinity rules. But here's what they tell us. If I change my motor speed, in this case it's represented by N, if I change my motor speed by half, for example, I should expect my flow to reduce by half, and that's what the first equation is telling me, that the proportion of change in speed is the proportion of change in flow. If I change my speed by half, I should expect my pressure to go to basically 1/4. So I'm dealing with the squared relationship. And likewise on power, my ratio of speed cubed is going to tell me about my power reduction. So if I've done a half reduction in speed, I'd expect my horsepower consumption to be 1/8 of what it was originally. So I've managed to make huge savings in horsepower just by a simple half reduction. And we saw that in the graph with the variable speed drive, that a 50% reduction in flow was bringing me down to about 20% consumption. But it's not all rosy. Not all end uses are created equal. The application on the left is one where we see variable torque and horsepower. So I'm able to change speed, and as I'm changing speed, I'm seeing the torque and horsepower respond. That's the kind of load that's following the affinity laws. So loads like this are centrifugal fans, pumps, blowers. And if I'm running a variable speed drive between 100% speed and 50% speed, I could be seeing really big savings out of that bunch. The second, what I've got here is a constant power load. So as my speed is dropping, my torque is actually increasing. This is the kind of load we're going to see on milling machines or lathes, drills. And this is not an application where a variable speed drive is actually going to do anything. What you need here is actually a specialized constant horsepower motor that's able to handle the higher torque requirement at lower speed. And variable speed drive is actually probably not going to work in this application. The third case, what we see is a constant torque application. So our horsepower is climbing as our speed's climbing, and the torque is remaining the same. This is the kind of thing you're going to see on the conveyor, extruder, mixer, positive displacement pumps. And you might here, in this case, have speed that varies drastically over a wide range, say like from 100% to 10%. Over that kind of range, you're going to see some pretty good savings at the lower end of that. So from when I'm getting slow, having the variable speed drive in there is going to generate my savings. So considerations then for your variable frequency drive or variable speed drive, concentrate on those centrifugal applications. So find those cases where you've got cooling water pumps in, and often what's recommended is it's the cycling of fluid out to cooling towers and things like that that's valuable, as opposed to circulating your process fluid out to your process, because that can tinker with a lot of different set points. But you got easy opportunities on cooling towers, the blowers, the variable air volume equipment, your heating, ventilating, air conditioning equipment. All of that kind of stuff is ripe with opportunities for variable speed drives. When you're dealing with the axial and reciprocating loads, you really don't have the affinity laws applying. So you don't have affinity laws. Much harder to predict your savings, but you will get some dollar savings in some cases from just reducing the amount of consumption. The other thing I want to point out here, just in the same section of considering the system, is that you really have to think about what the load requirements are. If you're running at one single constant speed, it really wouldn't make a whole lot of sense to invest in variable speed drive, because you're never varying the speed. I mean, that seems kind of obvious. Now looking at these two different graphs here, they look roughly the same. You can kind of see that on the surface, we've got a varying profile of different operating hours at different motor speeds and loads. In the left-hand graph, we see that the motor spends a fair bit of time at about 40% load, and then it spreads its time over the remaining loadings. This might be the application where you've got variable speed drive going on. So in this case, at 100%, motor's perfectly happy. You scale it down to speed where it's on 40% load. It's perfectly happy with that as well. And you're covering the whole range of requirements of the motor in the system. In the second graph on the right, if you look closely at it, you see really two different operating regimes. One where the motor is at about 20–40% of full load, and then you've got another where it's 60 and above. And if you can think back to that motor efficiency curve, remember that it was perfectly happy between 100 and 60 and 100 and really 50, and that its efficiency was maintained. And that might give you the idea here that you can use a motor that would be happy running at two different speeds, that maintain its efficiency on the loading that's between 100% and 60%, but at its second speed, which is more like the 40% load, it would be perfectly happy supplying the 20% requirement at the same time. And so there are specialized motors that will run two speeds or more in some cases, and that would be the application you want to apply that to. So you're matching the motor type and the motor drive to the different load profile you see. So an important tool for you. The third principle I want to cover is the idea that you need to plan. You know, here's the deal with motors. They're tied into your processes. And so, you know, while I've now gone through a series of background slides that can tell you why motor selection is important, why it can make good savings, and really it can, the reality is that measuring and evaluating systems in place is tricky. When your key piece of equipment's down, that's really not the time that you're going to begin evaluating whether you had the motor at the right size, what kind of efficiency it had. What you're going to do is you're going to reach for the fastest thing you can find. Hopefully it's the right one. Or you're going to put in a Band-Aid motor. It may be something that's too big. Your idea and what you say is that at some point later, when we get the chance, we're going to replace that motor and put the right one in. But I'll let you in on something that we find when we go out there, that motor that was put in the Band-Aid solution is rarely replaced. So years and years later, I'll go into a plant, and they'll say, oh yeah, 5 years ago that machine went down and we just put in that motor. We know it's too big, and that happens all the time. And it really, really costs you money. Remember that 80% of that lifetime cost is in that operating cost. So it's very, very expensive, Band-Aid. And frankly, you know, while we're out there looking around on the shop floor and talking to you, we will see that there's a very big motor in there, but not being intimately familiar with your processes, unless we're looking very, very, very closely at your system, we're not really going to have the background reference or perspective that you would have to be able to drop in a specific recommendation about the motor and how you're going to replace it. What we will say is we think you've got an opportunity in motors and that we need to take a closer look at that, and we really mean that. It's something that you do in a planning mode. It's something you do in a systematic mode where you're really looking at the overall system, the loads you're serving, and the overall plan and the plant for dealing with motors on an ongoing basis. So the idea then really with motor management plan is to lay in place a cohesive plan for managing your motor inventory. And that's to help you identify systematic ways to begin replacing the inefficient motor stock you've got, and to help you avoid those emergency Band-Aid fixes where you might replace with an inappropriate motor at some time when you're in a hurry. So let's take a quick look at what goes into motor management plan then. I mean, obviously the first thing you've got to do is survey what's out there. What equipment's out there? What are its ratings? What's it condition? What's it driving? What do we know about the systems in it? We also want to develop some guidelines to make some decisions about where there are opportunities to repair and replace motors that are at end of life, and I'll get to more of how you might find those in a minute. You also want to make sure you prepare for the eventuality that a motor is going to fail by creating a bit of an inventory of spares, and also by developing a bit of a specification and even some vendor relationships for motors so that you're able to quickly get your hands on the right replacement motor if you don't have it in your spares inventory already. So the spares inventory gives you a chance to source those motors that would be very difficult to get in a hurry versus the ones that you know you could get from a vendor in a hurry if you've got the right specification and you know exactly what you're after. You have to also get to the point of determining whether a motor should be repaired or replaced, and I also cover a bit of the tool for that. And finally, you've got to develop and implement a bit of a predictive and preventive maintenance program. So this gives you a chance to keep that motor inventory you've got in good shape for a longer period of time. And I've pulled up a bit of a case study here, which is the Reedy Creek Improvement District, which sends chilled water out to Walt Disney World facilities and has about 20,000 horsepower worth of motors. And so they used a DOE software tool to do the motor survey and track and identify what motors were in place. And so they pulled up a survey of about 120 motors at the North Service Area chiller plant. These motors were ranging from 25 to 700 horsepower. And primarily these were about water pumping, so chilled water, condensed water, municipal water, and some of the compressor and cooling tower motors. And what they found after their survey is in analyzing that deeper, they found 7 critical motors at the chiller plant and 1 at Disney. And those 8 motors together were 1,425 horsepower. And by identifying those and replacing those, they managed to achieve energy savings, which were over 300,000 kilowatt hours per year, about 60 kilowatts off the demand profile, worth about $30,000. So again, this sort of speaks to that idea of having a proactive repair or replace decision. So where do you begin if you're looking for those proactive opportunities? Well, why not start with the systems that are giving you trouble? They aren't functioning as they're supposed to, or they're constantly breaking down. If you're already in there trying to deal with those issues, why not do some overhaul of the system? Why not try to figure out what's going on with that, and at the same time get your equipment sized right and make sure everything's matched and nicely. You can also look for systems and components where you know the motors are due for replacement. They've been out there for 20 years. They're barely holding on, but you've kept them going. Now it's probably time to get some premium efficiency stuff in there and really look at opportunities for sizing. And you want to look for motors that are operating, over 2,000 hours a year, over 75 horsepower. The economics are going to work in your favor for replacing those. And then finally, because of those affinity rules, you're going to look for systems with blowers, pumps, fans, and compressors, and particularly those systems where you've got throttling devices in place instead of variable speed drives. And if you're looking at premium efficiency motors, here's some rules of thumb, just little guides you can use. When you're replacing motors that are near their end of life, like in the preventive maintenance program, or you've gone out and looked proactively, those are the chances to put in the premium efficiency motors. You're buying new. You can also look around for the old standard efficiency motors, so 15 and 20 years old. Don't rewind those. Get a premium efficiency motor in there and actually just get the right energy efficient solution in right away. Specify the premium efficiency motors when you've got new installations going in, or anything that's operating more than 3,500 hours per year, because the economics are going to work for your favor. And likewise, if you're buying new equipment, specify premium efficiency motors. The manufacturers can substitute these motors in, may have standard efficiency equipment in, but you can ask them to get that replacement. Because of the standard frame sizes, it should be fairly easy for them to find a replacement to put in there straight away. And if you've got motors that are operating more than 75% of the time, then also look for premium efficiency motors in those applications, because the economics are going to work in your favor. We want to talk also about preventive, predictive maintenance. A lot of causes for failure in these. Some of these are related to phase imbalance, so having the wrong or disparity in voltages between phases feeding a motor causes all kinds of currents in the rotor that heated up, in the stator that heated up, and that heat causes vibration. It causes premature wear of the motor, not good for it at all. And then mechanical failure is a really common one as well. Bearings that fail on about half of motor failures that are bearing related, but misalignment's also a big one. So if the shaft of the motor is in aligned precisely with the shaft on the load side, you might have vibration or unbalance that's also kind of shaking the motor apart. And finally, running the motor in an overloaded condition for a long period of time. So here you can see some of the standard causes of motor failure. And also just by looking for those, by actually consciously going out and looking for where a motor seems misaligned, maybe occasionally measuring voltage to see if the phases remain in balance, and doing this test which is shown on the right, which is a test of the insulation of the motor to verify the integrity of the insulation, essentially by putting a high voltage on the windings and compare the voltage that you've put on the winding against the frame voltage, and you can kind of measure how much resistance is still in that. And this graph is showing a case where they've measured every 6 months over a period of about 5 years the insulation resistance. You can see it holds quite well for about 4 years, and then in about the 5th year it begins to decline, and that's an indication for them at this point. They probably need to consider replacement of the motor or a rewind or something at that point. So they've essentially established a predictive replacement that they have to do. So, here's some of the sort of standard things. Look at the environment, make sure there's regular lubrication of bearings and rotating parts, looking for excessive heating and misalignment, measuring phase voltages, and measuring resistance of insulation. And ultimately, when you're doing motor management planning, you're going to come into this consideration of whether you send the thing out to repair or whether you try to replace it. And this curve that you see here is one that you'll find in a variety of reference sources, and it's built out of life cycle economic considerations. So it's looking at things like the cost to repair versus cost to replace, the efficiency of a repair, the energy cost in the local region, and so on. So all of those in. And the way you start using this curve is you start by drawing a horizontal line at your number of operating hours per year. So in this case, if we picked, say, 4,000 hours per year, and we moved horizontally out from that, right here, and you drag it out to the intersection of the nearest cost curve. So this is your cost per kilowatt hour of electricity. And again, I've put on this graph a 12.5 cents line, which indicates sort of that Ontario norm. You can see in the case of 4,000 hours that we come down somewhere around 60, 65 horsepower, if I just sort of draw down from that curve, as this decision point on replace and repair. And so the idea then is if my motor size falls to the right of that point, I'm going to want to replace. That's the economics are going to favor replacement. And if I'm going to the left, then I might want to send it to rewind. And there are some rules of thumb here we can apply. Again, the one is that if you've got a motor with defective stator core, don't rewind it. And if you can't restore that thing, just replace it with a new premium efficiency motor. If you've got a motor that's 100 horsepower or bigger and operates less than 4,000 hours, so essentially it's this quadrant here in the graph, that's one that you should try to rewind as long as your core iron is still within specification. If you've got a motor larger than 50 horsepower, you could rewind it really about 3 times, after which point you really should be thinking about replacing that motor. And the motors that fall between that repair-replace breakpoint should be replaced with the PEM and not rewound. Standard efficiency motors should probably not be rewound if you find that the cost to repair that thing is going to be more than about 60% of the cost of a new PEM, because at that point the economics work in the favor of replacing it. And a note on that, if you're going to send something out to rewind, not all shops are created equal. So I keep going back to this theme of not all things are created equal. And certainly in repair shops, you've got to do your homework with these. And in your planning, you should think about having a vendor or two selected to do your rewind work. You should be looking for international registrations. You should be expecting your shop to tell you about why the failure happened, give you a good report on that. And the expectation should certainly be that the shop is going to repair your motor to its original design. They should be able to repair or replace damaged cores. And this note about stripping occurring in an oven is that historically the insulation has been removed, the varnish has been removed from coils by dousing them in kerosene and lighting them on fire, which is really, really not good for the core of the motor, as you can imagine. So the idea is really to kind of be gentle about getting these motors apart and putting them back together. And you can also expect that if you bring your motor in and the shop has tested it, tore it down, given you a quote, and you say, well, I think I'm going to go and replace this motor somewhere else because, you know, gee, the repair cost you're giving me is at least 60% of a new motor. I think I should go and get a new one. It would be reasonable to expect that shop to charge you a bit of a fee for that test and tear down. I've included here at the last set of slides just some publications that you'll be able to go back and review that can that provide really excellent information on a lot of the stuff I've said. There's also some references to some software that you can use to track your motor inventory, create your motor management plans, and they're very, very useful. And with that, thank you very much, and welcome any questions that you might have.
Well, thank you so much, Herb. That was a great overview of motor management planning. We do have a couple of questions from the participants. The first one being, is there any comment on whether all premium efficiency motors are suitable to be used with variable frequency drives? Is this still an issue?
Okay, yeah, thanks for that. That's good. It's not something I addressed when I was talking about variable frequency drives in the presentation. Variable frequency drives are electronic controls. They're going to inject a bit of noise into your system, and not all motors are really able to handle that noise properly. In some motors, that's going to cause excessive heating or vibration. So there are motors that are rated for inverter quality that are basically well suited to that kind of drive, and some of your motors are going to do perfectly fine with that. This is a conversation you can have with your suppliers, manufacturers, vendors about, you know, what kind of compatibility you've got between drive and existing motor, or whether a new motor needs to go in. So yeah, that was an excellent question.
Oh, perfect. Great. So our last question is, what is the horsepower range for variable frequency drives?
The literature shows that the current upper range is around 100 horsepower, and variable speed drives will take you right down to fractional horsepower, but 100 horsepower about the standard now. There are probably some exceptions to the higher side, but at this point, that's generally where the mark is.
Perfect. Great. Thank you so much again, Herb. That was a great overview. And we thank all the participants for joining us again this month. And our next webinar is in the middle of March, so look forward to that. Thank you again and have a wonderful afternoon. Bye now.
Thanks all.